Alright, we're going to start the Chapter 9 homework review. This one will be pretty brief. As you'll notice, this homework assignment was pretty much 100% conceptual, which for the most part means you either knew it or you didn't. I will try to clarify a few misconceptions as we go through this, but for a lot of the questions you missed, your best bet to sort of understanding what went wrong is just go through the notes, go through the textbook, whatever helps you to try to review some of those concepts. And if you have any more questions, please, of course, come find me as always. But what we're going to do is just go through a few of the problems here that we had the most trouble with. There were a few problems on this assignment that also were worded pretty badly or set up incorrectly, whatever the case was. So I made a few corrections to some of your scores. You may notice that your homework score changed a little bit, but by and large it shouldn't affect things too much. Alright, so the ones we'll go over here, this one is something that is kind of knowledge-based, but it can be helpful to sort of rationalize a little bit. So if we have a primitive cubic lattice, each metal atom has how many nearest neighbor atoms of the same kind? So what we have to remember is that there's three types of cubic lattice. There's primitive, there's body-centered, and there's face-centered. And the names kind of tell you where the atoms go. So primitive cubic lattice only has atoms on the corners of the cube. So if we draw a quick cube here. So in a primitive cubic lattice, you only have atoms in the corners. There's going to be eight of those corners occupied. If you have a body-centered cubic, you have atoms in the corners and one more right in the middle. Face-centered cubic, you have one in each corner and just one on each face of the cube. So that's where the atoms go. And then these three structures differ with respect to their number of nearest neighbors and to the packing efficiency, which is the amount of space that's occupied by the atoms as a percentage of the total volume of the cube. So for number of nearest neighbors, for primitive we can kind of rationalize it. So if we think about an atom in the corner here, and how many nearest neighbors does it have, we can draw sort of a two-dimensional projection of this. So you have this top face of the cube is going to be bordered in all directions by other cubes. And so if we have an atom right here in the corner, it's going to have 1, 2, 3, 4 nearest neighbors that are in the same plane as it, and then it's going to have one directly above and one directly below. So you have one that comes out of the page, one that goes into the page that are also nearest to this one here. So for a primitive cubic, you have 6 nearest neighbors. Body-centered cubic is going to have 8. Face-centered cubic is going to have 12. So they differ with respect to the number of nearest neighbors, and probably the easiest thing to do to learn this is just to kind of memorize those differences. But for this one, we can pretty easily rationalize it by thinking about if you have an atom on the corner of a cube, and if that cube is surrounded by other cubes in all directions, how many closest neighbors does it have? The next two I'll go over are a couple of true-false questions where our success rate was less than 50%. So in other words, we did worse on this problem than if we would have just completely guessed. So the first one deals with very simple statement. Most metals occur as ionic solids. I remember that there's two types of solids that have metals in them. There's metallic solids and ionic solids. These are the two types we talked about where one of the components at least is a metal. Metallic solids are metals only, so you just have one metal in the structure, sometimes more than one if it's what we call a alloy or an intermetallic, but we didn't talk a lot of details about those. Ionic solids are going to have a metal paired with a nonmetal. So in this question we're asking most metals occur as ionic solid. We're just talking about metals by themselves, so those are going to all be as metallic solids pretty much. So most metals occur as metallic solids. This statement is going to be false because they don't occur as ionic solids. Really the only exception, the only metal that's not a metallic solid is mercury, which is a liquid at room temperature. But any other metal on the periodic table, if it's just a metal by itself, is going to occur as a metallic solid. And then the next true-false question had to do with atomic solids, and it says atomic solids generally have low melting points. Now, atomic solids, we haven't really maybe used this terminology a lot in class, there's two types of atomic solids. There's going to be metallic solids, which we just talked about. And then the other type of atomic solid would be a network covalent solid. So now the key point here is that for an atomic solid, you only have one type of atom. So these are all elemental substances that we're talking about, one type of atom. So metals are one classification of atomic solids, where it's a bunch of metal atoms arranged through metallic bonding. So that's sort of the type of bonding that's present in this. And then some non-metal elements occur as atomic solids as well, which are a type of network covalent solid. So these would be things like diamond, silicon, germanium, those ones that have that extended covalent bonding in all directions. I suppose graphite falls in this category as well. So these are just a few elements that have this type of structure, and in this case the atoms are held together by covalent bonding. Now the key point about both of these types of solids is that they have pretty strong interactions between the atoms that are holding them all together. Metallic bonding in the case of metals, covalent bonding in the case of the nonmetal network covalence. So both classes of atomic solids are going to have moderate to high melting points. Metallic solids tend to be a little bit lower, but in general you're going to have moderate to high melting points. So atomic solids generally are going to be moderate to high, so this is also a false statement. Alright? So the ones that have low melting points, those would be molecular solids. So we talked in class just earlier today about the four types of solids that we have: metallic, network covalent, molecular, and ionic. The only one that would typically have a low melting point is a molecular solid. All the rest are going to have moderate to high melting points, including both types of atomic solids. Alright, so the next one is also, in some sense, a true-false question. It deals with which of the following statements includes all that are correct, and deals with different types of close-packed structures. Alright, so for number one, 6 atoms in a plane always surround each atom in a closest packed structure. So remember that these closest packed structures, there's two of them. There's face-centered cubic and then there's hexagonal. They're both built from stacking layers of atoms in different ways, and these layers have spheres that are as close together as possible. So when you have layers of atoms all arranged as close together as possible, let's see how well I can do this drawing. Sorry, I messed that one up a little bit. When we place atoms into these close packed layers, where we're putting them as close together as possible, if we focus on one atom in that layer, let's say this one, and then I'll use a different color to color in its neighbors, in the same plane you're going to have 1, 2, 3, 4, 5, 6. So in the same layer you'll have 6 atoms surrounding each atom in a layer, so this one's going to be true. For number 2, we're talking about the repeating sequence of layers in closest packed metals is either AB, AB, or ABCA. This one is also true. So the AB packing gives us the hexagonal, and the ABCA gives us the face-centered cubic. Alright, and this again refers to how we stack the layers. So AB means you stagger the first 2 layers, and then the third layer eclipses the first. ABCA means you stagger the first 3 layers, and then it's not until the 4th layer that you put it directly on top of the first. But those are 2 different ways of stacking these close packed layers, like I just drew up here, and one of them gives you hexagonal, one gives you face-centered cubic. So this one is also true. And then finally for number 3, ABCA is the same as body-centered cubic, and where ABCA is going to be face-centered cubic. Body-centered is another type of AB, but but it's not close packed. In that case, there's a space between the atoms. Okay, so we talked a little bit in class about how we can stack layers to make these different structures. It's a little bit hard to visualize in 3 dimensions sometimes. But if you're talking about ABCA closest packing, that's going to give you a face-centered cubic structure. So this one's going to be false. We're talking about body-centered cubic, that would be an ABAB, but it's not one of the close packed structures. In that case, like I said, there's spaces between them. So the two that are true are going to be choices 1 and 2, so choice D would be the correct answer here. Alright, and then finally the last one I'll go through deals with counting atoms in a cubic unit cell, something we've talked about also in class quite a bit. So when you have a cubic unit cell, there are 3 different places you can put atoms. Okay? So we have corners, which count as 1/8 of an atom because they're shared by 8 different unit cells. We have faces, other faces. All these red ones are going to be face positions. They're in the center of a square face. There's a total of 6 of them. So those face positions are going to count as 1/2 because they're shared by 2 different unit cells. We have edge positions, each of the 12 edges. I won't draw all of them, but each of the edges, you can put an atom right in the middle. And those count as 1/4 because they're shared by 4. And then finally, there's one right in the center here that we can put, which is called the body-centered position. If I can ever get this color back. There we go. The one I drew in black is body-centered. Which counts as a full atom because it's directly in the middle. So those are the 4 different places we can put atoms in a cubic structure. So if we're talking about a body-centered cubic unit cell, what we have are 8 corners are filled plus the body-centered. So when we want to count the number of atoms, we have 8 corners, each counts as 1/8. Plus 1 center, which counts as a full atom. So we have a total of 2. So the one that represents this is going to be choice C, just written in a slightly different order. So when you have a body-centered cubic lattice, you have all 8 corners filled, counting as 1/8, and you have the center, which just counts as 1. Alright, so definitely review how to count atoms in a structure. I said this would be a short one. It looks like we're to the end, so please contact me with any other questions that you have.